Welcome back. In the previous videos, we introduced Carnot groups and the stratifications of their Lie algebras. I will now explain why Carnot groups admit dilations. Then I will equip them with some particular Carnot-Catahéodory distances. And then I will prove a theorem called the Ball-Box Theorem that says that in Carnot groups, boxes behave as some specific boxes, the balls, and in such a way that, as in the picture in my back, when the balls have smaller radius, some directions of the balls get squashed more than other directions. Okay, so let's continue our study of Carnot groups. Let's recall what Carnot groups are. Okay, so a Carnot group is denoted with G, is a simply connected Lie group whose Lie algebra let's call it G, admits and is equipped with a stratification namely a direct sum decomposition V1 ... direct sum Vs such that the bracket with V1 with Vs Vj is equal to Vj plus 1 for all j from 1 up to s, and then V1 bracket Vs is equal to 0. So this is a Carnot group. Okay, let's continue discussing this definition. Let's focus one moment why it's important to have it simply connected. So first of all, this means that given the Lie algebra, then there exists one and only one group with this Lie algebra. So let me just comment a little bit on the importance of having a simply connected Lie group. So the first thing, as I said, is the fact that there exists a unique Lie group G with Lie algebra G equal to G. But a second one, which will make use of it, is the fact that whenever you have a Lie algebra automorphism, homomorphism in general, homomorphism, then there exists unique Lie group homomorphism, such that the differential at the identity of this homomorphism is the Lie algebra homomorphism phi. This map can be seen as the tangent at the identity of this group homomorphism, or also as push forward on left invariant vector fields. Okay? Push forward on left invariant vector fields. Okay. At least it's well defined, the push forward, when these maps are really automorphisms. Okay. Now I want to stress that we're going to use this fact. Okay, why? The fact is that because of the dilations, we are going to have special maps which are for sure defined on the level of the Lie algebra, and we have to use this abstract fact to have the map, an induced map on the level of the group. So let me discuss an important one parameter family of Lie algebra homomorphisms. So what is this one parameter family? So let's fix lambda, a real number. And then we define the map delta lambda from the Lie algebra to itself. So remember that Lie algebra has this direct sum decomposition. Yes. Is the linear map, linear transformation, such that when restricted to the space Vj, this is the multiplication by lambda to the power j on this subspace. Okay, this is for all j from 1 to s. So in other words, right, if this is v1, this is v2, then a vector has the component along v1 stretched by lambda and the component along v2 stretched by lambda square, and it's going to be some kind of vector. All right, so now why is this map extremely important? Is because of this exercise that I leave it to you. So delta lambda is a Lie algebra homomorphism. In other words, delta lambda of x bracket y, this is equal the bracket between delta lambda x and delta lambda y. Okay. Why this exercise is true is a consequence of something we noticed last time, that if you perform the bracket between vi and vj, you get something that is inside vi plus j. Okay, so how do you prove this? You prove this by induction, okay, knowing that the bracket of v1 with vj goes to vj plus 1. So you solve this, notice this, and once you have this, then you notice that then this equation will be clear when you decompose the vectors with respect to the direct sum, because if this is multiplied by lambda I to the power I, this is multiplied by lambda j, then this bracket is inside the space, and therefore this bracket is multiplied by lambda to the I times lambda to the j, which is lambda to the I plus j. Okay, please try to do this exercise by yourself. All right, so we have for each lambda a Lie algebra homomorphism on the Lie algebra. All right, so now since the group is simply connected, there exists unique Lie group homomorphism, which we still denoted as delta lambda. Such that now we are denoting with the same symbol the same thing, but it should not be confusing. So the map seen as a group, as a group homomorphism, has the differential equal to the dilation on the level of the Lie algebra. Why this is not confusing is because I'll make you notice that in exponential coordinates, the two maps coincide. And this is because we know that for a group homomorphism, it commutes with its differential. Right? So we have this identity. Right? So up to exp, then the two maps are really the same. Okay. Then I put here the star. Right? So this is true for all automorphisms. Okay. Equivalently, one can define this delta lambda directly on the group. So equivalently, delta lambda from G to G is the only Lie group homomorphism such that the push forward of a left invariant vector field tangent to V1 is stretched by lambda. This is for all x in V1. The fact that it exists because of that stratification. The stratification. All right, so let's see what these maps are doing. So let's note a few things. So for all lambda, so if lambda is, we choose it between -1 and 1, then delta lambda is contractive. Namely, delta lambda iterated n times to every point, this converges to the identity in G. This is as n goes to infinity, and this is the iterated, is the iteration n times. Okay, and it's just because when you iterate lambda to the n, if lambda is a or Jn, then if lambda is a number less than 1, this converges to 0. Maybe before that, I should have said what happens when lambda is 0. So for lambda equal to 0, so delta 0 of every point, this is just the identity of the group. So it's the constant. And okay, what happens if lambda now has norm greater than 1? Then delta lambda iterated is expanding. So this is expanding, which, if you want, is the same of saying that the inverse is contractive, but this is the same of saying that if you iterate, then the sequence of points and they leave, the sequence leaves every compact set as n goes to infinity. Okay, let's see what is the presence of these dilations will tell us on the geometry of these groups. So first we have to equip them with some distance. Okay, let's equip Carnot groups with some particular distance. So distances. Distinguished class of distances on Carnot groups. All right. So, okay, we have our Carnot group with stratification V1 up to Vs. Now, an absolutely continuous curve gamma, defined on 0, 1, valued into G, is horizontal if we take the derivative of the curve, which exists almost everywhere. Now this is a vector at the point gamma t. Now we can bring it back via the left translation by gamma t. So now this is going to be an element that is a vector at the identity. Okay, let's define this vector, just gamma prime. So I will use the gamma prime for the vector brought back at the identity. So if this vector belongs not just to the Lie algebra, but the tangent at the identity, but to the subspace V1, and this is for almost every t. All right. So this is what is the definition of horizontal. Notice that one can equivalently say you have a subspace of the identity and now defines the left invariant tangent bundle that coincide with the identity with V1, and then gamma is horizontal with respect to this subbundle of the tangent bundle. All right, so now we are ready for the geometry, because now what we do, we fix a norm, and let's call it the symbol of the norm, on V1. Now, let's introduce the Carnot-Catahéodory distances. So, the Carnot-Catahéodory distance associated to V1 and the norm is nothing else than the distance function between, so the distance between 2 points, P and Q, is equal to the infimum of the length of horizontal curves connecting P and Q. Namely, the length of a curve is just the integral of the norm of the derivative, which is defined because gamma is absolutely continuous. So when gamma is an absolutely continuous curve that is horizontal. So horizontal, gamma 0 is P, and gamma 1 is Q. So gamma is defined on 0, 1, valued into G. Okay, so being horizontal, we have that this vector is almost all the time in V1, for which the norm is defined, and now the curve is absolutely continuous, and therefore this integral is finite almost. Okay, now, so this is the definition of a distance function. Okay, let's see some properties of this function. Properties. Okay, first, d is a distance. So it is obviously symmetric, that it gives distance 0 only when the 2 points are the same. It's obvious that satisfy the triangle inequality because you can join absolutely horizontal curves and have an horizontal curve. What is not completely clear is this is finite valued. Okay, so it's finite valued. And more than this distance really induces the manifold topology. And notice that with this fact, we will understand that then the topology is locally compact, because it's the topology of the manifold. To D is a geodesic distance. Hmm? 3, D is left invariant. So we have an isometrically homogeneous space. So here we have geodesic space. And the last point I want to prove is that each delta lambda is a dilation of factor lambda. Okay, so the fact is left invariant should be very clear because all the construction has been done left invariantly. Like really, like this, the length of curves, or even just already the definition of being horizontal is left invariant because you always bring back by left translation to the origin, and therefore the length is invariant on the left translations. Okay, so this is okay. Now these two parts are true in general because we are in the presence of a sub-Finsler Lie group. Okay, maybe I will discuss more for those that didn't study yet the definition of the structure of the theory of sub-Finsler groups. Okay, but let's maybe discuss more this property, which is the new property, really like this distinguish Carnot groups from arbitrary Lie groups. So what I'm saying is that so why is true? So why is this true? So delta lambda, remember, you see the map at the level of the group, go from G to G. So this is such that delta lambda of V is equal to lambda V for all V in V1. Now, if gamma is horizontal, then we can consider the tangent vector, which is an element of V1. So we can consider its norm. But now what about if we consider the dilation of the curve? Okay. Now this is another curve, and if you calculate the derivative, this is really is delta lambda at the level of the Lie algebra applied to gamma prime. Okay, it's chain rule. Okay, but this is an element of V1, so this is equal lambda gamma 1. All when you bring everything back at the origin. Okay, so when you take the norms, you exactly have that the derivative is stretched by lambda, and therefore when you calculate the integral of this quantity, you get lambda times the integral of the length of the initial curve, and therefore we have that when you infimize the curves between delta lambda p and delta lambda q, this is equal to lambda distance between p and q. And this is for all lambda and for all p, q in G. Okay, so please check that it's clear to you why we have this equality and consequently this equality here. This is going to be extremely important. On Carnot groups, we actually have a stronger statement than just the fact that the Carnot-Catahéodory distance induces the same topology. We can really have a quantitative bound on the behavior of the distance from the origin using the structure given by the stratification. Now I'll explain what I mean. The stronger statement I'm going to state goes under the name of the Ball-Box Theorem. So this is going to be the stronger statement than just being given the same topology. It's called Ball-Box Theorem. All right. So let's remember, we are talking about G Carnot group, and the Lie algebra is stratified V1 to Vs. And now let's fix a basis adapted to the Vj's, right? So I mean, we have V1 Vs, and this is going to be identified with Rm1. This is going to, will identify V1, and then V2 with some other, so maybe it's better to make it times Rms. So we have identified the Lie algebra with some Rn. Okay. Now, let me recall you this fact we already discussed. So this fact that on every simply connected nilpotent Lie group, as G is, then the exponential map from Rn to G is a global diffeomorphism. And when we identify the Lie algebra with Rn, we call it exponential coordinates. Fix the basis, we have what we call exponential coordinates. Exponential coordinates. So now on Carnot groups, we have special exponential coordinates, those for which the basis is adapted to the stratification. Okay, and in this basis, it's easy to write the dilations. So now recall that we have this dilation, and the dilation on the level of the Lie algebra. What do they do? I claim that this is a block diagonal. It's really diagonal. It's a diagonal. It's diagonal. Yeah, it's diagonal with blocks. So delta lambda is, okay, on V1, this is lambda identity on V1, and this is the first block. You can see this as a map from V1 to V1. Then the next block is a map from V2 to V2, which is the multiplication by lambda 2, and so on. At the end, we have lambda s identity on Vs. So this is a matrix, everywhere is 0. So in other words, I can write it delta lambda of at n-nupole T1 Tn is equal lambda T1 lambda Tm1. These are the components of B1. Then I have lambda square Tm1 plus 1 dot 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 lambda square Tm m1 plus m2 dot dot dot, and so on. Okay, so now we have this special map. Now let's see. Okay, so these are the elements that form V1. These are the elements that form V2. Okay, so now you see, if I take an element of the basis, no, say the jth element of the basis, this will be in some of the Vk. Okay, so let's give a name to this k. So for all j, let k such that ej belongs to vk. Call k d sub j, so we call the degree of the jth element, okay? And therefore what we have is that the dilation of the jth element is lambda dj times ej. All right, so now with having denoted these degrees, let me introduce the boxes. So the box of radius r is all the points in Rn for which the norm of the jth component is less than r to the dj. In other words, let me also write it like this. What we have is, you have minus tt, the interval minus tt, for as many times as the dimension of v1, so it's m1, times, now you have minus t square, this interval as many times as the dimension of m2, of v2, which is m2, dot, 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 minus ts, comma, ts, to the power ms, okay? Now, what is very important to notice is that if you dilate the box of radius r, you exactly have the box of radius lambda r. Okay? Now this should be very, very clear why this is true. Okay? I mean, you just multiply t. Now every element is dilated by lambda d. Right? So now you have this becomes the box where here instead of r dj you have lambda dj times r dj, which is the same as saying lambda r to the power dj. Okay, please check you have understood this, why this formula is true. Okay, but now notice this fact. I mean, this is exactly what we have for the balls, for the metric balls. We have the dilation of the balls at the origin of radius r. Because lambda is a dilation, then this is exactly the ball with radius lambda r. So you see that the boxes and the balls, they behave exactly in the same way under the dilation delta lambda. Okay, so what we conclude is the following. So let phi from Rn to g exponential coordinates with respect to a basis adapted to the stratification. Then the fact that we have the same topology, then this tells us that there exists some constant such that, okay, the box, let's take this, so this is an open set, I push it forward, this is still an open set, an open neighborhood of the origin. So this is an open neighborhood of 0, and when I map it is an open neighborhood of 1, and therefore it contains, for radius arbitrarily small enough, the ball at 1. On the other hand, this will be a bounded set, and therefore this is contained in the ball of radius of center 1 and radius some big constant c. Okay, so the same topology will give us this containment for these three neighborhoods of the origin, the identity point, the identity element. Now we apply the dilation invariance, and therefore we have that the ball radius r over c contains the boxes of radius r, which contains the ball of radius cr. Right? So how we conclude, so this is the statement of the Ball-Box theorem, which in words says that metric balls behave as inhomogeneous boxes. Where I mean with inhomogeneous, I mean that the size of the boxes, they are dilated differently according to the dilations. Okay, so we really have a bound on the behavior of the distance function. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.